In this lesson, we'll discuss some important concepts about fuel moisture sampling that will help you in your role as a fire effects monitor or field observer. We will briefly describe how environmental factors affect live and dead fuel moisture, and we will cover some key statistical concepts that are important to consider when measuring fuel moistures. These topics will provide a roadmap to follow when developing a sampling strategy for live and dead fuel moistures. In this lesson, we will cover the following aspects of fuel moisture sampling: environmental characteristics that influence fuel moistures, the importance of accurate fuel moisture measurements in predicting fire behavior and fire effects, methods for collecting fuel moisture samples in dead and live fuels, including soil and duff, and calculating and communicating fuel moisture values. These objectives tie directly to the tasks from the FEMO-FOBS Position Taskbook. Review the project objectives, monitoring plan, or management objectives as appropriate. Collect appropriate fuel, soil, and vegetation samples for moisture analysis. To start out, let's do a quick review of some of the fuel moisture material from S290. Recall that fuels can be classified as dead or live fuels, for obvious reasons. What's not so obvious is how these fuels differ in their reaction to weather conditions. We'll review these two classifications of fuels, the subcategories they can be divided into, and the factors that influence their moisture content. For the purposes of fuel moisture sampling, dead fuels include logs, twigs and branch material, forest floor litter such as pine needles and dead leaves, the duff layer under the litter, and mineral soil. Remember that dead woody fuels are classified into time lags, including 1 hour, 10 hour, 100 hour, and 1000 hour categories. Time lags express how rapidly these fuels gain or lose moisture in response to changing weather conditions. 1 hour fuels are small twigs between 0 and 1/4 inches in diameter. The 10 hour fuels are between 1/4 and 1 inch. And the 100 hour fuels are branches and logs between 1 and 3 inches in diameter. Fuels 3 to 8 inches in diameter are considered 1000 hour fuels, and logs greater than 8 inches in diameter are called 10,000 hour fuels. The moisture content of these fuels is directly determined by external environmental factors, causing the evaporation, condensation, and diffusion of moisture within the fuels. These physical processes are driven by factors such as the amount of sun the fuels get and their exposure to weather conditions. Solar radiation exposure is affected by the degree of slope, aspect, and elevation where the fuels are located. Solar radiation also varies by the time of day and time of year. The sun is most intense around noon and in the early summer months. Heating from the sun is also affected by the shading over the fuels from clouds and overstory vegetation. Recent weather also affects dead fuel moisture. High temperatures, low relative humidity, and wind increase evaporation, while precipitation is readily absorbed into dry fuels. These variables, such as air temperature, relative humidity, shading, etc., can easily be measured or estimated in the field. You used several of these measured values to estimate fine dead fuel moisture content in the weather observations lesson, and the fuel moisture content of larger dead fuels and other surface fuels can be roughly estimated from the fine dead fuel moisture. Dead fuel moisture will usually range between 1 to 30% because the dead plant cells are limited in their ability to absorb water. Live plant cells, on the other hand, have the ability to expand when adequate water is available. The moisture content of live fuels can range from 30 to 300% because living plant cells can contain more than their solid weight in water during some phases of their growth. For example, a new leaf in the spring can have 3 times as much water as plant material as measured by weight. Recall that the live fuel category includes herbaceous plants such as forbs and grasses that don't grow woody tissue, and woody fuels, which are shrubs that have woody stems and branches. Foliar fuels are the overstory tree foliage. For fire behavior purposes, only the moisture content of conifer needles are of interest. Mosses and lichens are included in this category as well. In some parts of the country, these overstory fuels are important contributors to fire behavior. In contrast to the dead fuels, The moisture content of live fuels is determined by internal physiological processes within the plant, and it's only indirectly influenced by environmental conditions. Many of the same environmental factors that regulate dead fuel moisture also influence live fuel moisture, but their impact on live fuels is indirect because the plant can regulate its moisture loss to compensate for current environmental conditions. Individual species have developed adaptations that allow them to regulate how much moisture they lose through evapotranspiration in response to current weather conditions. Moisture content in living plants generally follows a seasonal pattern, and changes are slower than in dead fuels. As we'll see, live fuel moistures follow this seasonal pattern from green-up in the spring to curing over the summer, and in some parts of the country, and with a frost kill event. The timing of these seasonal changes is greatly influenced by long-term weather patterns, such as drought conditions and available soil moisture. In this next section, we'll look at the importance of having accurate fuel moisture measurements. First, let's look at the role of fuel moisture values in fire modeling. Fire models are computer programs that are used to predict fire behavior and fire effects given a set of input conditions. Field measurements are often used as inputs to these models, and fuel moistures are important field-measured inputs. There are two broad categories of fire models used operationally as part of the fire behavior prediction system. Fire behavior models are used to predict fire characteristics such as the rate of spread, flame length, and intensity of a surface fire. They also predict whether a fire will transition into a crown fire. Fire behavior models use fuel moistures from 1 hour, 10-hour, and 100-hour dead fuels and all categories of live fuels as inputs, depending on the fuel models used. Fire effects models are used to predict fuel consumption, overstory mortality, smoke production, soil heating, and other fire effects. Fire effects models use 10-hour and 1,000-hour fuels, DUF, and soil moistures to predict fire effects. Both of these models require accurate fuel moisture values to make useful predictions. It is important to note that small errors in fuel moisture measurements can have large impacts on predicted fire behavior and effects. This slide shows an example prediction from a surface fire spread model for a grass fuel type using two typical measurements for herbaceous fuel moistures, 80% and 110%. Predicted rate of spread for this grass fuel type with 80% herbaceous moisture content was 33 chains per hour, whereas predicted rate of spread at 110% moisture content was more than 10 times less at 2 chains per hour. In some cases, models predict large changes in fire behavior for small changes in the measured inputs. Therefore, it's necessary to make the best measurements possible and to provide some error estimates of those measurements. Small errors in measurements might also affect the prediction of the type of fire that one might expect. Let's look at the example of conifer foliar moisture, which can be used to determine the potential of a fire to transition from the surface to the crowns. Differences in as small as 10% moisture content can affect the predictions. In the example shown here, assuming a crown base height of 4 feet and 3 foot flame lengths, the fire transitions to a crown fire at 90% foliar moisture content, but will not transition into a crown fire at 100%. Moisture content also influences how heat is transferred between materials, such as the stem of trees or the soil, and is therefore an important contributing factor to fire effects. Fuel moisture is an important factor controlling the consumption of heavy dead fuels, such as 1,000-hour fuels. This graph shows an example relationship between the 1,000-hour fuel moisture and the percent consumption of that fuel category. In general, as moisture content increases, dead fuel consumption decreases. Let's take a closer look at the seasonal pattern of plant development and how that affects fuel moistures. When growth begins in the spring, the moisture content of new plant material rises rapidly to a peak value. This peak value is often greater than 200% of its dry weight value. Moisture content in new growth will remain high as long as adequate moisture is available. During summer and fall, the moisture content decreases until it reaches a minimum level. This is known as curing in herbaceous plants and dormancy in woody plants. After the plant is completely cured, or gone dormant in the case of woody plants, the moisture level then remains at a generally low level until the growth cycle once again begins in the spring. In the early summer transition period, it is common to have fires that burn in the cured annual herbaceous plants, only to slow or stop spread when encountering perennial herbaceous plants. A fire in cheatgrass and running into native grasses is a good example of this. Take a moment to look at the graph of this seasonal pattern of live fuel moisture. We'll return to it again in the next section when we discuss why the accuracy of your fuel moisture measurements is so important. The presence of moisture in fuels affects fire behavior in two ways. During preheating, excess moisture must be evaporated before combustion can occur, and this process absorbs some of the heat of the fire. This means that there is less energy available to preheat adjacent fuels and to help propagate the fire. During combustion, moisture is driven off from the fuels and into the flames. Moisture dilutes the oxygen in the area around the fuel, and it cools the flame. Moist fuel acts as a heat sink, when the net result is a reduction in heat. Think of the fuel moisture as draining heat away from the fire. The result of fires burning into moist fuels is a reduction in fire activity. Dry fuels not only have less moisture available to absorb the heat of the fire, but when the fuels are dry enough to burn, they literally add fuel to the fire and increase the heat of the fire. Lack of moisture can cause fuels to become a heat source and contribute to increasing fire spread and intensity. Live fuel moistures are critical in predicting when seasonal changes will cause live vegetation to shift from acting as a heat sink to acting as a heat source. Accurate fuel moisture measurements can help fire behavior analysts and fire managers identify when this critical threshold occurs. This shift usually signals a rapid increase in local fire season activity. During the green-up period, live fuel moistures are high enough to cause a decrease in fire behavior as some of the fire's heat is absorbed in evaporating the water content of the plant. This is when live vegetation acts as a heat sink, absorbing some of the heat of the fire and slowing fire growth. At some point in the season, depending on the plant species, the plant will no longer have enough moisture content to slow the fire down and will actually transition to providing additional fuel to the fire. The plant now acts as a heat source for the fire, and it contributes to increased fire behavior. Different plant species cure at different rates over the season, and, as you can see from the graph, annuals typically lose moisture at a faster rate and cure to a lower moisture level than perennial plants. You may see an example of this on an early season fire in cheatgrass, an invasive annual grass common in the West. In the early summer transition period, a fire may burn actively in the cured cheatgrass only to slow or stop spreading when it burns into a perennial native grass with a much higher moisture content. Fuel moisture is an important determinant of fire behavior and fire effects. Remember that live fuels will react to moisture in the environment differently than dead fuels will. Relatively small differences in fuel moisture content can translate to significant changes in fire behavior and fire effects. This means that the accuracy of your fuel moisture measurements are important to producing reliable fire behavior and fire effects predictions. In the next section, we'll discuss the procedures to use in sampling fuel moistures so you can reduce the error in measurements. In this section, we'll discuss methods of measuring fuel moisture values accurately and how many samples to collect. First, a couple of basics about measuring fuel moistures. Recall from S290 that fuel moisture is the ratio of the weight of the water to the dry weight of the fuel particle. Because some fuels can hold more than their dry weight in water, fuel moisture values can exceed 100%. Generally, dead fuel moistures range from 1 to 30%, while live fuel moistures are usually between 30% and 300%. Note that when live fuel moistures are below 30%, the plant is considered dead and it's treated as part of the dead fuel component. Which fuels should you sample? The goal is to sample the moisture content of the materials that influence the way a fire will burn in those fuels. Selecting fuels to sample varies with the reason for sampling and the fuel type. Before you set out to the field to collect fuel moisture samples, talk to the fire behavior analyst, the long-term analyst, the burn boss, or the fire ecologist. Ask which fuel moisture values they are interested in. Is it the 1,000-hour dead fuel moisture? The live fuel moisture of the Gamble oak shrubs? Maybe they are interested in the foliar moisture of the Douglas fir and how it's affecting the potential for crown fire. Talking to the specialists who will use the fuel moistures you are measuring will help you collect only the information that will be useful. On prescribed fire, the burn plan will often specify a range of fuel moistures in critical fuel classifications. For example, the prescription may allow for burning when 10-hour fuel moisture is between 9% and 16%, and the live fuel moisture of the manzanita is greater than 80%. This would tell you that 10-hour dead fuels and the manzanita shrubs are the fuels to sample. Another way to determine which fuel moisture samples are needed on a longer-term incident is to ask the fire. Observe the fire as it spreads through the fuels and identify which fuels are burning and carrying the fire into unburned areas. Collect the fuels that are carrying fire and observe which fuels might be approaching critical fuel moisture content. Are the live Gamble oak too moist to carry fire today, but exhibiting color changes that indicate they're starting to cure? If so, collecting Gamble oak would provide the fire behavior specialists with valuable information. If you have access to the fire management plan for the area, many plans contain information about which fuel moistures are critical to fire spread for the particular area. This can be a valuable source of information when deciding which fuels to sample. In both prescribed fire and wildfire, try to anticipate which fuels the fire may burn into, especially if there is a change in fuel type or condition. Look outside the control lines to potential fuels the fire may spot into. There are several methods that are commonly used to estimate fuel moistures, such as calculating from weather observations, weighing standardized fuel sticks, using handheld moisture probes, or oven drying samples from the field. Each of these methods is effective for some fuel types, but none of them is appropriate for all fuel types. We'll cover how to use each of the methods, as well as which fuel types they're appropriate for. Small diameter dead fuels typically carry the fire and determine the rate of spread and intensity, so their moisture content is extremely important. These fine fuels, small twigs, conifer needles, dead leaves, and grasses, change fuel moisture quickly in response to environmental conditions such as temperature, humidity, and amount of solar radiation. It wouldn't be very effective to collect 1-hour fuel samples in the field, dry them in an oven overnight, and calculate their fuel moisture content the next day, because the fuel moisture content of the 1-hour fuels in the field could have changed significantly in the time it took to dry the samples. So the most effective way to determine fuel moisture content of fine fuels is to calculate it based on the environmental conditions that govern dead fuel moistures: temperature, relative humidity, aspect, slope, shading, time of year, and elevation. Does this sound familiar? You use these factors in a fire weather lesson to calculate fine dead fuel moisture and probability of ignition. Because fine fuels are critical drivers of fire behavior and change quickly with changing weather, fine dead fuel moisture should be calculated every hour as part of your regular hourly weather observations. Fuel moisture sticks are used as a substitute for natural fuels when calculating the moisture content of dead fuels in the 10-hour fuel moisture class. These 4 connected half-inch diameter ponderosa pine dowels are manufactured to specific tolerances with an oven-dried weight of about 100 grams. Once fuel moisture sticks reach equilibrium, their moisture content should be similar to that of natural fuels in the same size and will respond to changes in environmental conditions. The fuel moisture stick's initial dry weight, usually 100 grams, subtracted from its weight in ambient conditions, yields the weight of water in grams. Because the fuel moisture stick weighs about 100 grams when oven dried, the difference in weight also equals the percent fuel moisture. For example, if you weigh the 10-hour sticks and they weigh 112 grams, the fuel moisture content of the sticks is 12%, and the 10-hour fuel moisture for the present conditions can be estimated as 12%. 10-hour fuel moisture sticks are useful for helping to determine overnight recovery and daytime drying in fuels. Because their lag time is 10 hours, they only need to be measured once or twice a day. 10-hour fuel sticks are often used with manual weather station observations, where they are weighed around 1,400 each day to coincide with a daily weather observation. When using them on an incident, they can be weighed any time during the burning period, but be sure to place them in representative fuels several days ahead of your intended observations, so they have time to reach equilibrium with local conditions. Do not weigh the sticks if it's currently raining, or if there's free water beaded up on them. Moisture probes are handheld instruments used in lumber yards to measure moisture in commercial lumber. They're lightweight, portable, and relatively inexpensive, $150 to $500, but their effective range of 6% to 60% limits their usefulness to the larger dead fuels only, 100 plus hours and up. During a typical fire season, when the smaller fuels can be drier than 6% and live fuel moistures are greater than 60%, but they are extremely useful for getting quick readings for the larger dead fuels while in the field. Be sure to read the instructions for your specific model and note the accuracy range. The better probes are accurate to within plus or minus 1%. To take a measurement using the probes, saw the end off the branch you will be sampling using a hand saw and sample at several points in the cut end. Document whether your readings were from the surface, the outer edge of the cut end, or the center of the cut end. The larger fuels change more slowly in response to weather than the 1-hour and 10-hour fuels and have less of an influence on fire behavior, so daily measurements are unnecessary. An excellent resource for describing proper use and for comparing the accuracy of 10-hour fuel sticks and electronic moisture probes can be found at the link that appears on this screen. A common way to quickly estimate the fuel moisture of live fuels is a visual estimate based on plant appearance. This general approach is less accurate than the oven drying method, but it requires no equipment and produces instant results. When using visual estimation, focus on the live fuels the fire is currently burning in and the fuels it may encounter in the next few burn periods. As we saw earlier in this lesson, live fuel moisture content is highest as plants enter green-up and produce new foliage in the spring. Their moisture content can be as much as 3 times their dry weight during this period. As the leaves grow and mature, they gain additional structural weight, but the moisture content still remains above twice the dry weight of the foliage. The leaves appear young, and on perennials, these new leaves are brighter than older foliage on the same plant. After the new leaves mature and darken to match the older foliage, the moisture content will be approximately equal to the dry weight of the leaves, for an estimated live fuel moisture content of 100%. Important changes occur as plants enter the dormancy and curing stages, which can often signal the difference between live fuels not being available to burn and their becoming available fuels. Recall the discussion earlier about live fuels acting as heat sinks, as opposed to acting as heat sources. Are you seeing live fuels that would not burn last week now carrying fire? Observing and reporting this transition is important information for fire behavior specialists. Vegetation that is brown and dried will produce fire behavior similar to that of dead fuels because they are no longer capable of responding to changes in the environment by regulating their own moisture levels. While these changes generally occur gradually over the course of weeks, an underburn or frost kill can convert live fuels to dead fuels overnight. Make note of these situations and report conditions and color changes to overhead and fire behavior specialists. These quick and simple observations can yield important information critical to accurate fire behavior predictions and firefighter safety. The complete table for visual estimation of live fuel moisture content can be found on page 29 in Appendix B, 2006, of the Fireline Handbook or online at the link that appears on your screen. Next, we'll cover the oven drying method of measuring fuel moisture content. It's the most accurate method for determining fuel moisture in specific fuels, but it requires a significant investment in equipment and at least 24 hours to produce results. Nevertheless, if you have the equipment and the ability to wait a day for your results, it can be significantly more accurate than any of the other methods. Oven drying of field samples is a direct method for determining fuel moistures. You can collect the specific fuels you are interested in and measure their moisture content directly, rather than calculating or estimating their moisture content based on related information. To collect and dry the samples, you will need the following equipment: a drying oven, sample containers, a scale, and some hand tools, such as a set of clippers or utility shears, a trowel, and a handsaw. A cooler makes a handy case for your field equipment and provides a protected environment for the samples. Drying ovens, specifically for drying samples, are commercially available, but any oven that is able to maintain a regulated temperature of at least 140 degrees Fahrenheit will work. As mentioned, you'll need containers to store and process your samples. While aluminum sampling tins are commonly used, high-temp polypropylene bottles, aluminum paint cans, and self-sealing plastic bags also work well, although you will need a separate heat-resistant container to dry the samples if you use plastic bags. Prepare your sampling containers before heading out to collect samples. If the sample cans or bags have not been labeled previously, mark each container with a unique sample number. Cans and lids are easily engraved, and plastic containers, including bags, can be marked with permanent marker. Be sure to number both the can and the lid, and include a tare weight, the weight of the container itself, which will be subtracted when you are calculating your results. The containers need to be airtight to prevent the loss of moisture during the time between when you collect the samples and when you put them in the oven to dry. If the seal on your container is not airtight, bring tape to seal the container that will not leave a residue when you remove it. You'll also need a scale for weighing the samples. The same scale should be used both times the sample is weighed, before and after drying. A top-loading electronic scale capable of accurately measuring to the nearest 0.1 grams is adequate. These scales allow rapid weighing and are inexpensive. Battery-operated models for field use are available. Let's talk about some general guidelines for collecting fuel moisture samples in the field, and then we'll get to techniques for specific fuel types. When you arrive at a sampling site, place the sample case, the cooler, in the shade, and prepare your field data sheet. It's best to keep samples cool and dry, so leave the cooler and sampling equipment in the shade while you work. As with our other field observations, we'll use a form to record information about our sampling. Here's a sample form from the Wildland Fire modules. At each sampling site, record the location, by GPS if available, the date, time, observer name, observed weather, and site description, including elevation, aspect, slope, and cloud cover. A photograph of the site is also very useful to fire behavior specialists. In the comments section, note anything unusual or of special interest about the site. For example, are there irrigated agricultural fields nearby, or perhaps sudden changes in site characteristics that might affect your results? The rest of the form will be filled in when you return from the field to process the samples. Next, we'll cover techniques and tips for collecting specific types of fuel for fuel moisture sampling. We'll start with dead fuels. Remember from earlier in the lesson, we'll be calculating 1-hour fuel moisture from weather and site conditions, and we can use 10-hour fuel sticks to determine an estimate of 10-hour fuel moisture. For the purposes of determining fuel moisture on a prescribed fire or wildfire, the amount of time it would take to get results from the oven drying method makes it impractical to use for the smaller dead fuels, because by the next day, when you get your results, the moisture content of these fuels could be very different. Therefore, we'll just cover using the oven drying method for the larger dead fuels, 100-hour and 1,000-hour fuels. Do you remember what size diameter these fuels are? To sample these fuels, select a dead branch or log that is lying on the ground, not buried in dirt or duff, and that has not started to decay or crumble. Don't pick branches or trunks that appear recently fallen or that are dead but still attached to a live shrub or tree. Pick samples of different size within the time lag class. We'll discuss the number of samples to collect a little later in the lesson. Don't collect samples if it has rained in the past 24 hours. To collect a cookie, as the samples are called, use a handsaw to cut off the portion of the log that has been exposed to the air. Cut at least 6 inches from the end of a 1,000-hour log. Then cut a sample that is a ½ inch to an inch thick. Remove all lichen, moss, and very loose bark from the cookies. Place each cookie in a separate zip-sealed bag and seal it completely. Mark the bag with a unique sample number and record it on the form. Litter, duff, and soil are also within the dead fuel class. Litter is the uppermost layer of the forest floor profile. It's most easily distinguished from duff by whether you can easily recognize the original structure of the plant parts. Can you see mostly intact dead leaves and whole conifer needles in the material? Litter is generally not collected for fire behavior and fire effects prediction, as its fuel moisture will be similar to the 1-hour dead fuel category and will change quickly in response to environmental conditions. It's only important that you can recognize to distinguish it from the duff layer. The duff layer, on the other hand, is partially decomposed organic material lying below the litter layer. Its individual components are broken down enough that it's difficult to recognize individual plant parts. The duff component is often loosely held together by fine strands of grayish fungal material. While it's not used for fire behavior prediction, the moisture content of duff is used in fire effects modeling to predict fuel consumption, smoke production, and soil heating. To collect duff samples, brush aside the litter layer to expose the duff. Use a trowel to scoop up a sample and remove all live tree or plant roots from the sample. Try to avoid including soil particles in your sample. Your sample should be about 20 grams, about 3/4 of an ounce. Record the depth of the entire duff layer and the depth where the sample was taken. Okay, you're right. Soil is not technically a fuel, and it's not used in fire behavior models. But some vital plant parts are found in the soil layer, and soil moisture content greatly influences their heat exposure during a fire. Fire effects models use soil moisture to predict soil heating and plant mortality. The soil layer is identified by the fine mineral grains and lack of organic matter. If you're not sure, rub a small amount of the sample between your fingers. Soil particles can usually be felt and may be fine enough to fill the indentations in your fingertips. Sample the soil layer as you did the duff layer. Clear the layers above the soil, use a trowel to collect the sample, and place about 20 grams into the sampling container. Make sure there are no small rocks, animal droppings, or other organic pieces included in the sample. Record the depth where the sample was taken. For both duff and soil samples, the depth of the sample is very important and should be measured, not estimated. Next, we'll discuss each of the live fuel moistures we might be interested in sampling: herbaceous fuels, woody fuels, and foliar moisture. As you remember from the graph depicting the seasonal pattern of plant development, the moisture content of live plants changes very slowly from day to day, over the course of weeks, so sampling live fuels doesn't need to be done more frequently than every week, unless you observe changes in plant color or condition that would indicate a sudden change in fuel moisture content. When using the metal cans to collect live plant parts, fill each can about 3/4 full of loosely packed material. Replace the lid and seal with a non-residue tape, and record the sample number on the form. When collecting herbaceous samples, include the leaves and the stems of the plants. If there appears to be new leaves as well as older leaves, separate and label the new and old growth, and note this on your report form. For shrubs, collect only the leaves and small twigs of the plant. Pack the container 3/4 full, but make sure it's loosely packed. Spring-loaded twigs folded into the container can cause the top of the container to pop off and spill your sample. Collect leaves and twigs from different locations of larger shrubs: high, low, shaded, exposed, etc. But place samples from different plants in different containers, and note site differences on your log. Although the term foliar generally refers to all foliage or leaves of plants, for fire behavior modeling, foliar moisture refers to the moisture of conifer needles used to predict crown fire occurrence. So for foliar moisture, collect the live needles of conifer trees. Separate and label new and old growth. The old growth is the more important factor in crown fire. A couple of things to avoid when collecting your samples. If rain, dew, or other surface water is present on the fuel you want to sample, don't collect the sample. Wait until later in the day or the next day after the free water dries up. Shaking the sample to remove excess water or attempting to dry the sample in any way is ineffective. Don't mix fuel types, such as live fuels with dead fuels, grasses with twigs, moss with 10 hours, etc. Put just one fuel type in each container. For predicting fire behavior, we're only interested in grass, leaves, needles, stems, twigs, and branches. Don't collect berries, nuts, flowers, seeds or seed pods, or similar non-fuel plant materials. So how many samples of each fuel should you collect? Sampling costs time and money, but so do errors in estimating fire behavior and fire effects. So we need to be as efficient as possible with the resources and time available. There are ways to calculate the number of samples needed for high levels of accuracy, but for time-constrained incidents, such as prescribed fire and wildfire, a minimum of 3 samples for each fuel type will be sufficient to start with. We'll discuss how to express the variability within the 3 samples at the end of this lesson. You can collect more samples if you have the time and oven space. Once samples are collected, they should be weighed in the field, if possible. This ensures that no moisture loss occurs from the time the sample is collected and the time of weighing. Keep the filled sampling containers in a cool, dry place until you get back to your workspace to process them. Ideally within 24 to 48 hours. Preheat the oven to between 60 degrees Celsius, 140 degrees Fahrenheit, and 93 degrees Celsius, 200 degrees Fahrenheit, and be sure to note the temperature used on your form. Weigh the sample cans with closed lids and record the wet weights. Then remove the lids just prior to placing the containers in the oven. If you spill material, re-weigh the sample. Dry the samples for 24 hours, 48 hours for very wet samples. You may have to weigh wetter samples several times to ensure that their weight is stable and that there is no more moisture to evaporate in the sample. Replace the lids immediately after the samples are removed from the oven to prevent the dry samples from absorbing any atmospheric moisture. You did number the lids with the same numbers as the containers, right? Weigh each sample and record the weights on the form. Remember, weigh the wet sample with the lid on. Dry the sample with the lid off. Weigh the dry sample with the lid on. If you previously marked the container with the empty tare weight, you can use that as the tare weight for the sample in that container. If not, you will need to weigh the empty container to determine its tare. Once it's measured and marked on the container, the tare weight will not vary much throughout its lifetime, but should be verified occasionally. Cans may be cleansed after use. Usually they can be wiped with a dry cloth, but occasionally they may need to be cleaned with a solvent to remove pitch or sap. Now we have the information needed to calculate the fuel moisture content for each sample. Remember from earlier that fuel moisture is the ratio of the weight of water to dry weight in a fuel particle. So we can calculate the weight of the water by subtracting the weight of the dry sample from the original wet weight, and then calculate the weight of the dry material by subtracting the weight of the container, tare, from the dry sample weight. Divide the weight of the water by the weight of the dry sample and multiply by 100% to get the percent fuel moisture content. Let's look at an example. We have a sample of Gamble oak shrub in a sampling tin that weighed 22 grams before we dried it. After we dried it in the oven for 24 hours, it weighed 12 grams in the tin. The sampling tin weighs 4 grams empty. So, the weight of the water that evaporated in the oven was 10 grams, the difference between the wet and dry weights. The dry weight is the weight of the dried sample in the tin minus the weight of the tin, or 8 grams. If we divide the weight of the water by the weight of the dry material, we get 1.25, and when we multiply by 100%, the percent fuel moisture content is 125%. Think back to the seasonal pattern of plant development graph. In what stage of development is the Gamble oak? What time of year is it? Based on the visual indicators of live fuel moisture, what would you expect the leaves of the Gamble oak shrub to look like? If you have access to a spreadsheet program, you can build a simple spreadsheet to easily calculate this for you, and avoid making hand calculation errors, which is one of the most common sources of error in measuring fuel moistures. There are many sources of potential error with this method. Care in collecting the samples and in processing them will help you produce the most accurate and useful fuel moisture measurements, which will result in more accurate fire behavior and fire effects predictions. But even under the best of circumstances, it's basically impossible to measure fuel moistures precisely, due to the many sources of variability and error. The task, therefore, is to measure fuel moistures as carefully and accurately as possible, and then to communicate these measurements along with some idea of how accurate the measurements might be. Next, we'll cover what to do with these numbers to provide firefighters, fire managers, and fire behavior specialists with a description of the fuel moisture values and how much confidence they can have in those values. To do this, we must understand a few statistical concepts that will help us communicate to others our field measurements and their accuracy. The simple procedure we are going to present here is based on collecting 3 samples of each dead fuel size class of interest, 100 hour and or 1000 hour, or 3 samples of each live species of interest, species that are carrying the fire or expected to carry the fire. Each sample should come from a different individual plant or piece of downed wood. Next, we'll discuss the 2 main statistical concepts that you must understand in order to adequately sample fuel moistures and communicate those measurements to others. These include the mean or average and the range. The mean, or average, is a measure of the middle of a range of observed values. The range is a description of how far apart the minimum value and the maximum value are. The average is calculated by adding up all the values and dividing the total by the number of values. The range is calculated by subtracting the largest observed value from the smallest observed value. Although these measurements are quickly calculated using a computer or a spreadsheet, they can also be easily calculated in the field using a handheld calculator. Let's look at a couple of examples of calculating the average and the range of 3 observed fuel moisture values for foliar moisture. You have 3 samples of live needles from a Douglas fir, and the values you calculated after drying them in the oven are as follows. Sample 1, 104%. Sample 2, 94%. Sample 3, 99%. The average is calculated by adding all 3 values together and then dividing by the number of samples, 3 in this case. The range is determined by subtracting the smallest value, 94%, from the largest value, 104%. What is the average and the range of the foliar moisture for Douglas fir? You should have gotten 99% for the average and 10% for the range. These 3 samples tell you that 1. Not all Douglas fir trees you sampled have the same foliar moisture, and 2. While the values are not the same, there is not a lot of variability in the foliar moisture. But what is not a lot of variability? Is it enough variability to lower your confidence that the average of 99% is an accurate estimation of foliar moisture in Douglas firs in the area you sampled? Let's look at a tool that can help you express how much confidence you and other fire decision makers should put in your fuel moisture content values. This chart is a simplified version of the sample size calculations. It shows you whether or not 3 samples are enough to measure the mean value to within plus or minus 5% of the mean. To use the chart, first calculate the mean and range for the fuel moisture samples of a given fuel type or species. Find your mean value on the x, horizontal axis, and follow the line up until you reach the range of your observed sample. If the point falls below the line, then you have collected enough samples to estimate the mean fuel moisture content to within plus or minus 5% of that mean value. If the point is above the line, you need more samples to accurately estimate the mean. You can either use your results to figure out how many more samples you need using a standard formula for calculating sample size, and then return to the site to collect more samples, or, if you won't have an opportunity to revisit the site to collect more samples, you can communicate to the users of the fuel moisture information that your results have a lower confidence level than you would like, and that they should be used with appropriate caution. In the case of our 3 Douglas fir samples, find the calculated mean fuel moisture value, 99%, on the x-axis, and follow that point up until you intersect the line for the range value, 10%. In this case, the results of our 3 samples fall below the line and are thus adequate to measure the fuel moisture to within plus or minus 5% of 99%. When you use the sample size chart properly, you can be confident that you have taken enough samples to measure the mean to within plus or minus 5% of the mean. For example, if you have 3 samples of bunch grass whose mean fuel moisture is 40% and the range is 5%, your results will fall below the line, indicating that you have an adequate number of samples to say that you have a high level of confidence that the actual fuel moisture of the bunch grass is between 38% and 42%. If the graph indicates that the 3 samples are not adequate to express the variability of the fuel moisture values, and you are not able to return for more samples, indicate the mean and the range of the 3 samples and communicate to the users of the information that the values indicate that more samples should be taken and that the results should be used with caution. This can be helpful to fire behavior specialists and fire managers who may have multiple sources of conflicting information about fuel moistures. While this process may seem cumbersome at first, think about the difference between reporting a single fuel moisture value with no indication of how reliable it might be versus reporting an average within a range and an indication of how accurate it might be. Most fire managers would prefer to know the level of uncertainty associated with the information they use to make their decisions regarding strategy, tactics, and safety. In review, here's the process to use for measuring fuel moistures and communicating the results in a meaningful way. Take 3 samples of a given fuel type and calculate their moisture contents. Determine the mean and range of the moisture content samples. Use the sampling chart to determine whether 3 samples are enough to estimate the mean moisture content to within 5%. Report fuel moisture values as a range and communicate the reliability of the results. In this lesson, we looked at why fuel moisture is important, types of fuels and their moisture content, and factors that influence dead and live fuel moistures. We talked about which methods to use with different fuels, collection techniques, how many samples to take, and how to communicate the results. Strengthening your skills in determining fuel moistures can give you and the firefighters and managers you work with important and reliable insight into how changes in fuel moisture can affect the fire environment. How will this impact the decisions you make on the fire ground?